So in this lesson, we want to find the derivatives and figure out how to use them for a few very kind of special functions. We're going to look at the sine of x and the cosine of x, so a couple of the basic trig functions, and then we'll look at the exponential function e to the x, and then also our natural logarithmic function, natural log of x. So for sine of x, I want to go ahead and work its proof. It's relatively straightforward. I like doing the proof of this because one, it reinforces the limit definition, and two, it actually uses a couple of statements that we did back in Unit 1. And so if I want to find the derivative with respect to x of sine of x, that's what I want to do. I want to say if I have the function sine of x, what's its derivative? Well, let's write this out as the limit definition. This is the limit as h approaches 0 of sine of x plus h. That would be f of x plus h, is having x plus h as the argument of sine, minus the sine of x all over h. So the next step, and there's going to be a couple moments here where there's just some kind of intuitive things that I'll help walk you through what you would stumble into. You've got the sine of x plus h. Algebraically, nothing can happen with it in the sine of x. This is not a situation where you can factor out a sine of x or anything like that. However, you spent a lot of time in pre-calculus learning your trig identities. And one of the reasons why is because we can take, this is called the angle addition for sine identity. If I have sine of something plus something else, in this case x plus h, what I can actually rewrite it as. And so I'll do this here. The limit as h approaches 0. The sine of x plus h is equal to the sine of x times the cosine of h plus the sine of h times the cosine of x. So the sine stays the same for addition. I still have a plus here. But it's the sine of one thing times the cosine of the other, and then it's the sine of the other thing times the cosine of the other. That's what that angle addition identity you learned for sine looks like. So this is sine of x plus h, and then I want to subtract off the sine of x, and this is all over h. So we learned a couple of interesting trig limit statements back in Unit 1. We talked about the limit as h approaches 0. We said the limit as h approaches 0. Since we're talking about h, it would be sine of h over h was equal to 1. If you take a look here, I do have a sine of h. So I'm going to kind of let this piece play by itself. Because I have this single term in the denominator, I want the part that has the sine of h over h to be by itself. So let's write that as the limit as h approaches 0. I'm going to take this middle piece, and hopefully when I'm done, you'll see that algebraically I haven't changed anything. I'm just rewriting it. So the sine of h cosine of x over h. So taking this term over h, writing it out, and then let's see what happens when I have what's left. So this is plus the limit as h approaches 0 of the sine of x cosine of h. So there's that term minus the sine of x over h. So just kind of a little rewriting using that identity and then separating in a way because I really want to get this guy by itself. And then this one's also going to take the form of something that we've looked at here in the past. So let's rewrite this as the limit as h approaches 0. I'm going to let sine of h over h take charge. This is a known limit statement from Unit 1 times the limit as h approaches 0 of the cosine of x. So I've got that split up, and this is nice because this is actually a value that we know. Over here, and this is where a little bit of intuition has to happen, I look at the numerator and I see that I can factor out a sine of x from both terms. And in fact, what I'm actually going to do, because we have a limit statement actually that says the limit as h approaches 0 of 1 minus the cosine of h over h is equal to something, I'm actually going to factor out not just sine of x, I'm actually going to factor out negative sine of x so that I can write this with the other, kind of go in the other direction here in terms of what's being subtracted. So if I factor out negative sine of x, like so, And then that is going to be times the limit as h approaches 0. Okay, now think about what I did. I wanted to do that, so this is going to be just simply 1 now. And if I factor out a negative sign from here, this is 1 minus the cosine of h all over h. And the reason why I wanted to factor out a negative sign of x is because I wanted to generate this statement right here, because this is also a known limit value for us. From unit 1, we said that this limit right here, the limit as h approaches 0 of sine of h over h, we used the squeeze theorem to show that that was equal to 1. Now the limit as h approaches 0 of cosine of x, notice that there is no h here. In fact, in terms of h, this is actually kind of a constantly behaving function. And so the limit as h approaches 0 of cosine of x, there's no h to substitute in. That's just cosine of x. The same is true right here when I take the limit as h approaches 0 of negative sine of x. That's equal just to negative sine of x. And then this particular limit statement right here, the limit as h approaches 0 of 1 minus cosine of h over h, we said in unit 1 that this was equal to 0. And so if you take a look at what we get here, I get the cosine of x. And that's it, because 0 times negative sine of x is 0. So this is the proof that the derivative of sine of x is equal to the cosine of x. And that's kind of a convenient thing, and it's kind of an interesting thing that happens mathematically. That when we describe the rate of change of that sine wave, it's actually described by the cosine wave. That's kind of a neat relationship between sine and cosine. So the main takeaway here, I walked you through the proof, but understand that the derivative of sine of x is equal to cosine of x. So the next thing we're going to do is we're going to prove what the derivative of cosine of x is equal to.